Hey guys, it's Miss Maneely, and I'm going to go ahead through the AP Statistics Midterm Review Guide. Because we spent some time in class and I've already had the answers displayed on Blackboard, I'm not going to go through every single problem. I'm going to create two videos, one describing data, that's Unit 1, and we'll talk about both one variable distributions as well as two variable distributions, and then I'm going to do a second video that goes over the probability rules and random variables. I think the Unit 2, the planning, the study, I think what I've written out is probably self-explanatory. Certainly, if you have any questions, you can come see me, early Monday morning or during Bulldog Block on Friday if you have any questions, or I guess not Monday, but Tuesday. All right, so like I said, I'm going to jump to problem number 5 with the one variable distributions. Oops. And I'm not really going to talk about how to do this problem. You're given a set of data. You're asked to construct a Boxwhisker plot and determine if there are any outliers. This is something that I know most of you, if you're given data, know how to plug it into your calculator. If you go to Stat and then press Enter, you can enter all the values into a list. And then if you go to Second Stat Plot, choose one of the plot options. You can just select the first option for a Boxwhisker plot, and that includes your outliers. So if you're given a set of data, that's all you have to do is just construct a modified Boxwhisker plot on your calculator. Your calculator will graph it, you can hit trace, and that'll give you your 5-number summary as well as your outliers. What I didn't put on here was an example of what to do if you are just given the 5-number summary and asked if there are any outliers. So I'm going to give you an example of what that might look like. All right, so suppose I give you a 5-number summary. So that's the min, the Q1, the median, a Q3, and a max. All right, so let's say my min is 50. Let's say my Q1 is 80. Let's say my min is 80, or my median is 82. Let's do a Q3 of 90 and a max of 95. Okay, so if that's my 5-number summary and I want to calculate whether or not there are any outliers, I need to remember my outlier rule. If I have a low outlier, that means it's going to be below Q1 minus 1.5 times the interquartile range. If I have a high outlier, that means it's going to be above Q3 plus 1.5 times the interquartile range. So if I plug in what I know Q1 is 80. I'm going to do minus 1.5. The interquartile range I know is 90 minus 80, which is just 10. And so this is going to be 80 minus, 1.5 times 10 is going to be 15. And 80 minus 15 is going to be 65. Do I have any values that are less than 65? Yes, my min is less than 65, so that is a low outlier. When I'm doing my high outliers, I'm going to plug in Q3, which is 90. And then do plus 1.5 times 10, or 90 plus 15, which is 105. And since my max is only 95, I don't have a high outlier. Since my max is not above that number, it's not an outlier. Okay. The next problem I said I would do is number 7. And this is a normal distribution, so I'm actually going to make sure that my calculator is up so we can do this together. So number 7 is the snack pack of potato chips is advertised to weigh 3.5 ounces. The weights are normally distributed with a mean of 3.5 ounces and a standard deviation of 0.2. For a snack pack of potato chips, determine the proportion of snacks that weigh in the given intervals. So I'm going to call X my weights. Remember, if this is a free response question, you want to make sure that you define your variable and then describe how it's distributed. So I know X is distributed normally with a mean of 3.5 and a standard deviation of 0.2. If I'm trying to find the proportion that weigh less than 3, I'm looking for the probability that X is less than 3.0. That's my X value. If this is a free response question, then you also have to translate it into a Z-score. So remember, our Z-scores, and this is part C of number 6, is going to equal our observation minus the mean over the standard deviation. So in this case, that's going to be 3 minus 3.5, and I'm putting that in parentheses, divided by 0.2. And I get a Z-score of negative 2.5. At this point, I can go ahead to my normal CDF, which is second vars, and that's the second option there. And you can do this two different ways. If I'm using my X variable, which I can do. Since I'm dealing with a less than probability, my lower bound is going to be negative infinity. The calculator already has this in here as -1e99. That's the same thing as -999999999. My upper bound, though, if I'm using my x variable, would be 3. But the mean and standard deviation of x is not 0 and 1, so I'd have to adjust it to 3.5 and 0.2. And if we press enter, we get the probability of 0.0062. Okay. If I'm doing a multiple choice question, I don't have to worry about standardizing it. I can just go straight to the probability. And obviously you don't really have to write anything down. This time we're looking at more than 3.7. Remember, a normal distribution is continuous, so I don't have to worry about whether or not there's an equal sign associated with the inequality. So if I go to my distributions, normal CDF, this time, since I'm looking at a greater than, 3.7 is going to be my lower bound. My upper bound is going to be infinity, so I'm going to do a positive 99999. You could also do 1e999, whatever. And my mean is still 3.5. My standard deviation is still 0.2. So it makes it a little bit easier. If you're doing multiple choice, you don't have to go through all the steps. So the probability here would be 0.1587. And if you're doing between two values, all that's going to do is change your lower bound and your upper bound. So I'm not going to worry about going through that one. In letter D, though, it's asking a different question. It's saying Snack Pack completes periodic quality control inspections by randomly selecting bags from each batch. The company will discard the entire batch if the selected bag falls below the 10th percentile of weights. For what weights should the Snack Pack discard its bag of chips? All right, or its batch of chips. So I'm going to draw a picture here. If I am discarding the 10th percentile, or the lowest 10th percentile, that means I'm discarding this group of batches right here, and that means there's 10% there. I know that my mean is 3.5. I know my standard deviation is 0.2, and I'm trying to figure out the x value. What weights of chips are going to correspond to that value? Well, in order to do that, if I think about my formula, so I know the mean, I know the standard deviation, I'm trying to solve for x, so in order for me to do that, I need to know what z is. Well, I can figure out what z is since I know the area, but this time I have to work backwards. So since I'm given the area, when I go to my distribution menu, I'm going to choose the inverse normal operation. When you're using this, it's always referring to the area on the left, which is what I'm given. So I'm going to go ahead and put in 0.1. Now, if this were a free response question, you'd keep the mean as 0 and the standard deviation as 1. So I'm going to actually go ahead and do it this way. And that gives me my z-score. So now I know that the z-score associated with that point is negative 1.282. So now I have enough information to solve for x. So if I have negative 1.282, and that's going to equal x minus my mean, which is 3.5, times the standard deviation, which is 0.2. So I basically just need to multiply by 0.2 and add 3.5. And that gives me my x value. And if this were a free response, I'd want to make sure that I'm saying they would discard batches less than 3.24 ounces. Okay. And if this were just a multiple choice question, I'll show you, you can jump right to that answer by choosing the normal or the inverse normal operation. The area is still 0.1, but if you enter in the mean of 3.5 and the standard deviation of 0.2, the calculator will give you the x value. You don't have to take that extra step. Number 8 is very similar. It says, suppose the mean of a normal distribution is 20 and 45% of the observations fall, I guess that's above the standard deviation. Sorry, it's a little cut off. Again, I'm going to draw a picture. This time I know 45% of the observations are going to fall up here. And I know the mean of my distribution is 20. And I think that's all I know, right? We're trying to figure out the standard deviation. Oh, wait, I do know that, let's see. Yeah, this number is 30. It just got cut off on my smartboard. So 45% of the observations are above 30. So I do have enough information. I'm given the value of x this time. So here, let me rewrite the formula. I've got z equals x minus the mean over the standard deviation. So this time I know x, that's my 30. I know my mean, and I'm trying to solve for the standard deviation. So again, I've got to figure out the value of z, which I can do using my inverse normal operation. But remember, when I put the area in, I have to put in the area to the left. So these values here correspond to my x values. My z values, remember the mean would be 0, and I've got to figure out the corresponding z value for that 55 or the 55th percentile. So if I go to second distributions, and in this case, since I don't know the standard deviation, I have to find the z-score. So this time I'm going to put in an area of 55%. This time my mean, I have to put it in as 0 and 1 because I don't know the standard deviation for my x variable. And so I get a z-score of 0.1257. And that's going to equal 30 minus my mean, which I know is 20, divided by my standard deviation. Well, this is just a proportion. If I multiply both sides by sigma and divide by 0.1257, I'm going to have 30 minus 20 over 0.1257. And so I'm just going to do that all in one step. 30 minus 20. And then I'm going to divide by, I don't want to have a rounding error, so I'm going to use my second answer shortcut. And that gives me a standard deviation, which is really, really big. And that's 79.579. And I cannot even think of a real-life situation that would have a mean at 20 and a standard deviation of almost 80. That's pretty unrealistic. All right, so let's go ahead and move into two variables. I'm going to do number 9. This has to do with calculating the least squares regression line given the summary statistics. So we're given information about the mean and the standard deviation of both variables, as well as the correlation coefficient, which again is sort of cut off. Let me see if I can make this a little bit smaller so we can see the whole problem. There we go. All right, so to calculate the least squares regression equation, you have to remember how to calculate the slope and the y-intercept. These formulas will be on your midterm, the formula sheet that you'll get with your midterms. If you're wondering what other forms are available, if you look in your book towards the back, you'll see where like all the normal distribution tables are. There is a formula sheet there, and those are the formulas that you'll be given on your test. But the slope formula is there. The only problem is it doesn't call itself the slope formula, so you have to be able to recognize that that's what it is. And I think it's referred to as like B sub 1 or something. I'm just going to write out the word slope just so that we don't get tangled up in the notation. The slope, if you think about it, is rise over run, and rise measures the change in y, and run measures the change in x. Well, if we think about our summary statistics, the variable or the value that measures change would be our standard deviation, because it's talking about a difference. So I'm going to look at my standard deviation of y over the standard deviation of x. But remember, standard deviation is always positive, and so if I'm going to have a negative slope, I've got to figure out a way to introduce the direction of my line, and I do that by multiplying by my correlation coefficient. And so now I know that my correlation coefficient is negative 0.218. My standard deviation for y is 10.135, and the standard deviation for x is 1.974. And I guess I should probably talk about what this problem represents. We're looking at whether or not the row number affects test scores in a classroom. And so obviously I'm going to end up with a negative slope here, and the value you should get is negative 1.1193. You're asked to interpret this value. With slope, it's always as x increases by 1 unit, y is expected to either increase or decrease by the value of the slope. Don't forget to use units as well, because you want to make sure you put it in context. So in this case, what we're saying is as the row number increases by 1, the test score is predicted to decrease by 1.19 points. To find your y-intercept, well, let's think about our equation of a line. You're used to probably y equals mx plus b. Whoops. All right, well, we just figured out what m is, our slope. If I want to solve for b, I know that my y-intercept is just going to be y minus mx. So my y-intercept is going to equal a y value minus the slope times the corresponding x value. So I've got to figure out a point on this line. One thing you do need to remember is that x bar, y bar is a point on every single regression line. So this formula changes like that. And since I'm given the mean of x and the mean of y, I can plug everything into my equation. So I know the mean of y is 81.2. I'm going to subtract my slope, which happens to be negative, so don't get scared that you have a double negative. And then I'm going to multiply by the mean of x, which is 4.033. And when I do that, I get a y-intercept of 85.714. And you're asked to interpret it. So that basically means that if I were sitting in row 0, that my expected test score would be about 85.7% or points, or however this is measured. It doesn't really say, I don't think. Okay. Number 10, this is an example of computer output. You're also given a scatter plot and a residual plot for the relationship between the 40-yard sprint time in seconds and the long jump distance in inches for a small statistics class of 12 students. So it asks you to identify the explanatory and the response variables. In this case, it's probably easiest to just look for them in the graph. So remember, our explanatory variable is always x, our response variable is always y. So in this case, x represents our sprint time. And our response would be our long jump distance. It says to calculate the correlation coefficient. So remember, that's the r value. We're not given r, but we are given r squared. That's this number here. Make sure you change it back to a decimal before you figure this out. So if I want to find the value of r, I'm going to have to take the square root of 0.702. And so when I do that, I get 0.8379. But this is one thing that you have to be really careful of. If I look at that line, it's decreasing. So I know that my slope must be negative. That means that my correlation must be negative because there's a negative association between the variables. So don't forget to include that negative when you're doing this. And then once you compute the correlation coefficient, then you can comment on the association between the variables. And remember, when we're dealing with two variables, we talk about the strength, direction, and the form. So you would definitely want to say that there's a negative association between sprint time and long jump. The longer the sprint time, the shorter the long jump. You would want to say something about how strong you think that association is, and it looks, moderately strong. And you'd also want to comment on its form, and in this case, it is fairly linear. We don't see a curve in the pattern. Letter C asks you to write the equation of the least squares regression line and then comment on the appropriateness of the data, or of the model for the data. So in this case, I'm going to go back up to my computer printout, and I'm looking at those two numbers underneath where it says coefficient. The number that's next to the word constant is my y-intercept. So I've got 414.79. The number that is next to my other variable, remember, sprint is my x variable, so the number that's next to my x variable is my slope. So I'm going to have minus 45.74 times x. And then it asks you to comment on the appropriateness of the model. There are a lot of different things that you can say about it. For example, you're given the residual plot. So one thing you might want to say is that because there is a random scatter of points above and below the regression equation in our residual plot, that the line is appropriate for the data. You could look at the r squared value, which you're actually going to have to interpret in letter F. You could also look at the standard deviation of the residuals, which we're going to look at in letter E. But in this case, we've got a fairly moderate to strong correlation coefficient. We can observe the residuals, and it seems like a pretty appropriate model. In letter D, it says to calculate and interpret the residual for Christian who had a sprint time of 7.25 seconds and a long jump of 110. I want to apologize because on the answer sheet that I did, I was just estimating what Christian's predicted long jump would be. You really do want to actually plug in. So this is the actual x. This is his actual y. If I plug the actual x into the equation, so if I take 414.79 minus 45.74 and multiply that by 7.25, this is going to give me Christian's predicted long jump. So 414.79 minus 45.74 times 7.25. All right, we get 83.175. Okay, so to calculate the residual, we always do the actual minus the predicted. Okay, that's similar to when we were doing calculating the z-scores. We take our actual observation minus the mean, which is what we would expect or predict to be. So in this case, my actual long jump was 110, or Christian's actual long jump was 110, and the prediction is 83.174 or 175. So if I subtract, again, I'm going to do second answer, we get a difference of 26.825. And then you may be asked a question, does our model overpredict or underpredict our, or overestimate or underestimate our value? And because our prediction is less than the actual, then we know that we are underestimating. Letter E asks you to interpret the standard deviation of the residuals. Remember, our residuals measure the distance from between the actual and the predicted. So the standard deviation of our residuals is just going to be our average prediction error. And in letter F, when it talks about the coefficient of determination, that is your 70.2%. And we're saying 72 or 70.2% of the variation in our y variable, and the y variable in this case is our long jump. And we'd say can be explained by or predicted by the regression equation on our x variable, which is sprint times. Okay. All right, last one. Number 11 for this video, and then we'll jump to probability. In number 11, it says, how is braking distance for a motorcycle related to the speed the motorcycle was going when the brake was applied? Statistics teacher Aaron Wagner gathered data to answer this question. The scatter plot to the right shows the speed in miles per hour and the distance in feet needed to come to a complete stop when the brake was applied. So you can see that there is a very slight curve to the data. And so this problem deals with transformations. So in letter A, it says the graphs below show the result of two different transformations of the data. The first graph plots the log of the distance against speed. So this is, this is the log of the distance, I believe. And this is our speed. So this would be x versus the log of y. And then in the other one, we've got the log of x versus the log of y. So we've got the log of the speed versus the log of the distance. And so you're asked, what kind of model would be most appropriate? This is where you want to look for the linear association between the transformed data. And so I can see that the second graph is the most linear. And so I have to think about the function that it would be associated to with the log of x and the log of y. And that's going to be the power function. If you remember, if it's x times the log of y, if that's the straightest association, you're going to do exponential regression. If it's the log of x versus y, this is where you're going to do logarithmic. And if it's the log of both, remember pow pow, we do our power model. Letter B gives you the computer printout or the output for the regression analysis. Remember, all of our computers use linear regression. So this is still the same linear regression output that we looked at the other problem. So again, I can write a linear equation where we have y hat is equal to, that first number represents my y-intercept because it's next to the word constant, and the other number represents my speed, or I'm sorry, my slope, because it's next to the independent variable. And that's going to go next to x. But I have to define my variables. So remember, I'm looking at this association. This is the linear equation that I just came up with, and now I've got to define my variables. Well, x in this case corresponds to the log of the speed, and y is going to correspond to the log of the long jump distance. You could also just include I could actually just write this as the log of the distance is equal to negative 1.35 plus 2.036 times the log of the speed this way, and then I'm defining my variables within the equation. Okay, so that's it for video 1. The other video I'm going to post will be for the probability unit.